Okay, so now we move on to what we mean by modeling, okay? We now understand what we mean by various examples of CFD, but to really do computational fluid dynamics, you have to take the first step. You have to model the problem using mathematical formulations, okay? Using mathematical formulations in terms of initial boundary value problem. Okay, but what is an initial boundary value problem? Well, the initial boundary value problem is a form of a partial differential equations with appropriate or with supporting boundary and initial conditions. In order to do the CFD analysis for the aerodynamics over an automobile, we need to come up with a mathematical formulation of the fluid flow over the car. And so you apply the conservation of mass, the conservation of momentum over the car. You will have to apply a boundary conditions. How do I apply the boundary conditions? Well, you have to have a region in space where you're going to do that analysis. Does the problem involve initial conditions? In other words, at time zero, what is the environmental condition? Is everything stagnant? Is it raining? Okay. Is the temperature very high? Or are we at room temperature? If I want to do a CFD analysis as a result of superimposing these air conditioning systems in this room, we need to start out with a situation where, well, the temperature, there's no air conditioning in this room, and so the temperature is high, above 21 degrees Celsius. Now, then put in the air conditioning system, turn it on, the air conditioning system is set at, say, 17 degrees C. How does the temperature in this room basically vary with time? How long does it take for the temperature of this room to reach a comfortable temperature for the inhabitants? Okay, so that is what we mean by initial value problem. Okay, what is the initial state of your system, and what are the boundary conditions that impact the solution of the differential equation? Now, in modeling in CFD, this includes first understanding of your geometry and your domain where you are going to solve the problem. Okay? You have to know your geometry and the region or the place, the area that you are going to solve the problem. You have to understand what coordinate system to use. Okay? You have to understand what coordinate systems to use. You have to understand the governing equations that you have to use or you have to apply. You have to understand the flow conditions. You have to understand or know the initial boundary conditions, and then the selection of models for different applications. So every CFD problem will have a pertinent model that is germane to it, that can be applied to it. Let's look further into the geometry and the domain. Simple geometries can easily be created by a few geometric parameters. For example, if you have a pipe, okay, if you are analyzing flow in a pipe, what coordinate system do you think you have to solve the problem in? Cylindrical, right? So if you recall, when you were taking your fluid dynamics, when you are solving pipe flow problems, you use the cylindrical coordinates to solve the pipe flow problem in determining the pressure drop. Okay? On the other hand, if you have a rectangular channel instead of a circular pipe, if you have a rectangular channel, then you would use rectangular coordinate system in order to solve the problem. Okay? Now, you can also have complex geometries. These must be created by partial differential equations, or, as in today, using 3D scanning or importing database of the geometry, e.g. the airfoil, into a commercial software. Now, what do I mean by this? A pipe is an easy system to represent, right? What if you want to analyze the heat transfer of the electronic chips in your computer? Okay? How are you going to do that? You see, in CFD, we always have to come up with a geometry. That geometry requires us to be able to represent it pictorially using a drawing. Okay? In some cases, yeah, you can just use straight lines to represent it. In some cases, you have to use really curved, complicated structures. If I take a look at this speaker,
line in.
if I take a look at this speaker, if I'm to draw it, it's a complicated structure, okay? But now, thanks to technology, we can use a 3D scanner to scan the object and then import it into a commercial software, and instead of you, the engineer, using your drafting techniques to really draft it, okay? That is why, at least in the US, we've stopped teaching drafting, okay? Because you can easily create objects using various softwares and also using 3D scanning techniques. Okay, you scan. My whole body can be scanned such that it's imported into the software, and they can do CFD of my body mass of my body mass. Okay, that's what I mean by complex geometries. Okay, and of course you have to have a firm understanding of the size and the domain. Are we doing the CFD over a prototype car, an entire car? Are we doing the CFD over a bus? Are we doing the climate weather analysis over the whole of Kumasi or over the whole of Ghana? Okay, that domain and size becomes important because that impacts your computational resources. Okay, so here are typical approaches that are used in geometry and domain analysis. We do a lot of geometrical approximations. We use computer-aided design and computer-aided engineering integration software. So these are some of the softwares, including AutoCAD, including Solid Edge, okay, and other softwares in order to generate the computer-aided geometry of the object. And then we have to have an understanding of whether we are going to use the Cartesian coordinate system, of course, the rectangular coordinate system in X, Y, or Z, the cylindrical coordinate system in the radius, the circumferential angle, or the axial distance Z, or the spherical coordinate system, again, the radius, circumferential, or azimuthal angle phi. One has to choose the appropriate coordinates to solve the problem. Okay, so this is just giving you a breakdown of what I mean by the different coordinate system. So in other words, if I'm solving the problem in the Cartesian coordinate system, then my governing equations have to be written in the Cartesian coordinate system. If I'm solving the problem in cylindrical coordinate system, then the governing equations has to be transformed into a cylindrical coordinate system. If I'm solving a spherical coordinate, if I'm solving a problem in spherical coordinate system, then the governing equations has to be transformed into a spherical coordinate system. So, question. You want to analyze the temperature as well as the pressure forces in a storage tank. Okay? How many types of storage tanks can we have? Anyone? How many different types of storage tanks configuration can you design? Okay, your water storage tank. How would you classify that? Cylindrical, right? Okay. Or your storage tank can also be rectangular. Okay. In a lot of process industry, you also have spherical tanks. Okay. So this is what I mean. Depending on the nature of the problem, we can either use, if it's a rectangular tank, then we are going to use the Cartesian coordinate system. If it's a cylindrical tank, then we are going to use the cylindrical coordinate system or spherical coordinate system. Okay? So you have to really have a firm grasp as to the geometry of your problem in CFD as you design it. Okay? And in some cases, there may be some coordinate transformations that may be required. Now, how many of you have seen these equations before? Do you remember them? Okay, so when you see, in the beginning, I gave you the pictures of a lot of famous scientists, right? Well, two famous scientists, Navier and Stokes, came up with these equations. Okay? Later on, I'm going to derive them for you, okay? But for now, I basically present to you the three-dimensional Cartesian coordinates representation of the Navier-Stokes equations. The first equation basically represents the equation in the x direction. The second equation represents the Navier-Stokes equation in the y direction. And the third equation basically represents the equation in the z direction. I mean, they all look similar apart from the fact that you have a u term on top and a v term here in this second equation and a w term here. What is the significance of u, v, and w? What is the significance? What is the significance of saying that, well, this is a representation of the Navier-Stokes equation in the x direction? What is the significance of u in this equation? Now, Navier-Stokes equation is what? An expression of the momentum, right? But what is momentum? Mass times velocity, right? So if this is an expression of the momentum equation in the x direction, what is u? Velocity in what direction? X direction. Very good. So similarly, this is the v here is the velocity in the y direction, and w will be the velocity in the z direction. Okay? Now, in all these equations, the first term, which has to do with the rate of change, the partial rate of change of the velocity in the partial rate of change of the velocity, and of course, rate of change of velocity is what? Acceleration, right? So the first term represents local acceleration in the x, y, and z direction. These three terms that comes after the local acceleration are what we call the convective or convection terms. Okay? How the mass of the fluid is pushed, okay, within the pipe, for example. It's convected within the pipe. Okay? Convection is nothing but forcing a fluid to flow over a surface. And then we are saying that, well, the local acceleration and the convection of the fluid has to be balanced by the piezometric pressure gradient as well as the viscous terms or viscous forces acting on the object. Okay, we have a class?
Yes, some students have.
Oh, some students have class. Okay, so we've done 1 hour already. Mm-hmm. Right. Yeah. Okay. So let's give a pause for that interchange, and then if you have any questions, ask. Yes.
Then in terms of the notation, you have just u subscript x, u subscript y, and u subscript z for the different velocity in the different
Yes. 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 So this would be this u would be ux. Yeah. Okay. Well, okay, what happened? Well, you see, okay, so the velocity vector has 3 components. Okay, the velocity vector has 3 components: u, v, and w. So basically, that is your x, y, and z. So it's the decomposition of those components in the 3 directions of the momentum equations. Okay? Now, okay, so for those of you who are just walking in, we have started a discussion on what we mean by computational fluid dynamics, okay? And we talked about how computational fluid dynamics can be applied across various spectrums of engineering applications, such as aerospace engineering, marine engineering, biomedical engineering, or biomedical application, environmental applications, and so on and so forth, okay? These notes would be available so you can go back and review those applications. We also talked about what we mean by modeling, okay, which is basically the starting point of doing any CFD. Okay, if I want to do any CFD, I have to come up with my mathematical representation of the problem. Okay, and then a numerical solution of that mathematical representation of the problem. And of course, that mathematical implementation of the problem has to be cast in the form of an initial value problem. That is, it must have initial as well as boundary conditions. So when you were taking your differential equations or your calculus class, you see your professor will give you a differential equation, he will give you some boundary conditions and an initial condition, and he says solve it for the dependent variable. Okay? So all that we are saying here now is that instead of your professor giving you those differential equations and the boundary and initial conditions, now you, the computational fluid dynamics scientists, have to come up with your model, your differential equation representation of the system, and then determine the boundary conditions for you to solve it. And so in this case, all that I'm demonstrating here is one of the means of doing that is by coming up with, say, the Navier-Stokes equations, which is an expression of the momentum equation applied to a given fluid flow system. Okay? And then we can also apply the continuity equation, which basically represents the conservation of mass applied to a given fluid flow system. Okay? In applying the conservation of mass and also conservation of momentum, you may need the equation of state. Okay? For example, in compressed flows, okay, you may need the equation of state to be able to cast the pressure in terms of the density, the ideal gas constant, and the temperature. Okay, or you may need, for example, this Rayleigh equation, and when we write the energy equation, you also need other equations such as Fourier's law, Fick's law for diffusion. Okay, you need all sorts of equations to fully capture or model your CFD problem. Any comments or questions? Okay, let's move on. So based on the physics of the fluid phenomena, CFD can be distinguished into different categories using different criteria. Okay? One, we are saying that, well, why is all of this important in being able to distinguish between different criteria? You, the engineer, have to have that understanding, particularly when you are using different softwares, okay, to solve the problem. Okay? If I'm using an ANSYS Fluent or I'm using a COMSOL software, any CFD software that you can think of, or I am basically writing my own CFD, I'm doing my own CFD programming from scratch. After I have basically determined the mathematical formulation representing of the physical system, I need certain simplifications in order to solve the problem. Okay? Knowing those simplifications helps me to basically distinguish between the different categories or the criteria that has to be applied in the solution of that CFD problem. And so these are just examples of some of the simplifications or the criteria in classifying CFD problem. First here, we have to distinguish between whether we have viscous or inviscid. Okay? If it's viscous flow, then we don't have to worry about the viscous terms in, you see, if it's viscous flow, then we don't have to worry, then we have to take into consideration the viscosity in the momentum equation. But if we say, well, the problem is inviscid, we can neglect viscosity, then that means that this whole term can be dropped. Okay? The viscous forces can be dropped from the solution. If the problem is internal or external, remember the example that I gave, okay, where we're looking at, the release from the floodgates in a dam, okay? That is an open channel flow, okay? So we'll classify that as an external flow. But if the flow, or another example of external flow is the flow over an aircraft, okay, over the jet F-18 aircraft, or the flow over an automobile. Okay, those are all external flow. We are looking at the effects of the fluid flow over the structure in it. Okay, on the other hand, if it's an internal flow, that is the flow is within a confined, bounded region, then we have to classify it as such and solve for the flow inside the pipe or inside the tank. We have to also distinguish whether the flow is turbulent or laminar. Okay? The RE basically here represents the Reynolds number. Okay? You can use the Reynolds number, if you recall from your fluid mechanics, to classify whether we have turbulence or laminar. And so let me see if you remember the difference between laminar and turbulence for a pipe flow. What is the transition from laminar to turbulence in a pipe flow? What is that Reynolds number? 2,100, 2,300, okay? Very good, okay? So this is all we are saying here, okay? Quick back of the hand calculation in doing your analysis, you establish that, well, we don't have to worry about turbulence. We are just dealing with laminar streamline flow in the system, okay? So we have to decide that. We have to decide whether we have incompressible flow or we have compressible flow. Okay? In that case, the Mach number helps us determine whether we have incompressible flow or compressible flow. Okay? Do we have single or multi-phase flow? Okay? Do we have single or multi-phase flow? In that case, CA represents the cavitation within the system, within the pump. Okay, where single flow could be you have water and its vapor, or multi-phase. Multi-phase means you have water and its vapor, or single means that you just have just the water flowing in the system, or just liquid flowing in the system. Whereas multi-phase can be gas and liquid. Okay, and then we have to think of thermal and density effects. Okay, why is density effect associated with thermal? Let's get the students to give us an answer. Why do we associate density with thermal? Why is that important? What happens to warm air? It expands, it rises, right? Okay, so in a given problem, we have to know whether we have thermal implications, because those thermal implications tells us that we also have to consider conservation of energy within the system. Okay, so not only are we solving continuity, that is conservation of mass and the conservation of momentum, we also have to consider conservation of energy. Free flow and surface tension effects can also be important within a given system. Okay, the Froude and the Ware number in terms of free flow and surface flow, and then the Peclet number in terms of chemical reactions and combustion. Okay, so, and this is not the end of be all or end all of all of this. This is just saying that you have to clearly understand the category or the nature of the system that you are solving so that you can use the proper formulations in the computational fluid dynamics. Okay? If the fluid is non-reacting, then of course you don't have to worry about chemical reaction and combustion. But if it's reacting, then you have to worry about chemical reactions. Then you have to introduce Fick's law and other laws into your governing equations. We continue with modeling now. We want to drill in particularly to initial conditions. The initial conditions basically impact your unsteady flow and your steady flow. Okay? The initial conditions should not affect your final steady results. Why is that? And your initial conditions only affect convergence path. Why is that? Your final steady result, basically, you are saying that for time into infinity, your environment remains static, constant. The conditions of your system does not change. Okay? So if the conditions of your system does not change, then it is steady state. Okay? You have a steady state process. Okay? But on the other hand, if your initial condition, okay, is going to impact your solution at every time step, then it leads to an unsteady flow problem. And so you have to pay attention to your initial conditions. Okay? And your initial conditions that you set also affects how your solution basically converges in terms of iterations. You see, when you start your computation, you don't smoothly arrive at steady state. Okay? It may take you some oscillations within your solution to arrive at your steady state. And so we say that your initial conditions needs to reach at a converged solution. So it is important how you basically select or specify your initial state of your system. Okay? And you have to basically develop the experience of coming up with reasonable guesses to speed up your convergence of your solution. Now this part here is understanding the numerics, okay, and basically understanding the numerical solution process and be able to make accurate prediction or guesses in terms of how to obtain a converged solutions. Now, for complicated unsteady flow problems, CFD codes are really run in the steady mode for a few iterations for getting a better initial conditions. What this means is that, if I know that I'm going to have an unsteady problem, I'm solving an unsteady problem, the easiest solution is actually solving the steady state problem. Okay, assuming that your system stays the same at all times. So if you start with the steady state solutions, at least let's say that I want to find the temperature of this room based on this air conditioning. What is the steady state temperature that I want to attain in this room? Well, if the steady state temperature, right now I'm looking at my AC, it says 19 degrees C. Okay, it says 19 degrees C. That means that I want the steady state temperature of this room to be 19 degrees C. But if the AC is turned off, because of the environmental conditions, you know this room is going to warm up, right? And so the temperature might be, let's say, around 22 degrees C. And so our initial temperature is actually 22 degrees C. Okay, that is our initial temperature. So if I'm modeling the process, then my initial temperature should be 22 degrees C. On the other hand, I know that if my final temperature is going to be 19 degrees C, then I shouldn't pick a very low temperature because that would lead to a lot of inconsistencies in my result. It won't allow me to reach at my steady state solutions quickly. Are you guys with me? Do you follow me? Okay. So let's look at this flow in a pipe. Okay. We can look at it from the three-dimensional view sense. Okay. You have flow entering here and flow leaving. And we can also look at it in a two-dimensional sense. Okay? By two-dimensional sense, I'm saying that, well, I know I have symmetry, right? So I have symmetry along the axis. Okay? And so if I have symmetry along the axis, that means that in the solution of this pipe flow, I can use an axis symmetric representation of the pipe and still get reasonable results. That saves computational time instead of solving the full three-dimensional problem. Okay? Because in the full three-dimensional problem, that means that I have to solve the full Navier-Stokes equation for momentum in all the three dimensions. Okay? Whereas in this case, I only have to worry about the axial and the radial dimensions. Okay? Now, what are the boundary conditions? Well, the boundary conditions that we normally consider in solving pipe flow is the no slip or slip free on the walls. Okay? Periodic and inlet condition. What we mean by inlet condition? We have velocity inlet, mass flow inlet, constant pressure. And the outlet condition, we have constant pressure, velocity, convective, zero gradient. Now, let's see what we mean by these. This is the inlet, right? Likewise, in this axis symmetric representation, this is the inlet. So in the inlet, we are saying that the velocity in the x direction, u, is some constant value c. Okay? The velocity in the x direction, u, is fixed at some value c. However, there's no flow moving upward, right? At the inlet, the flow is just horizontal. The flow is being pumped into the pipe. And so then I know that the velocity in the y direction is 0. All right? At the inlet. At the outlet, I can fix a constant pressure at the outlet. Well, I can say that at the outlet, the pipe is exposed to atmospheric pressure. If the pipe is exposed to atmospheric pressure, well, then this P is equal to C, a constant is just atmospheric pressure. Okay? And then another boundary condition, because I've reduced this to an axisymmetric flow, that means that, you know, what happens on top is the same as what would happen on the bottom side. Okay? It's symmetrical. So then at the line of symmetry, the velocity is 0. Okay? Or the pressure gradient at the line of symmetry is 0. The rate of change of the velocity in the radial direction is also 0. Okay, yes? Okay, why is the velocity 0 at the line of symmetry? Basically, we are saying that the velocity inside the pipe, the velocity enters constant inside the pipe, okay? And if you were to draw the velocity profile, you know, particularly with no slip condition, you see that it will be somehow parabolic. Okay, it will be parabolic. I wish I had something to draw it. It will be parabolic, so we are saying that, you know, well, there will be variation of the velocity radially, but when you come to r is equal to 0, it is 0. Well, this is the v velocity, not u velocity. Okay? Inside the pipe, there is velocity variation in all directions. Okay? But the vertical component is 0. Okay? So that's a good question, good point. Okay? And similarly, the pressure gradient at that point is also 0. And you have rather to your point about the fact that we have to have maximum velocity in the axial direction. The u velocity has to be maximum. That is why du, dr is 0. Okay? All right. Any comments or questions? Now, in terms of selection of models, basically CFD codes typically designed for solving certain fluid phenomena by applying different models, okay? Again, we apply whether we are going to have viscous versus inviscid, turbulent or laminar. If you have turbulent flow, then you have to have a turbulent model. Okay, you have to have a turbulent model. Now the question is, why do we have to have a turbulent model? Well, let's go back to our Navier-Stokes equation. If you have turbulence, then that means that these velocities are fluctuating. Okay? They are not uniform. So the question is, well, if the velocities are fluctuating and are not uniform, then how do I capture accurately the velocity in my momentum equation to accurately determine these viscous forces in my fluid? Okay? We have to come up with an appropriate turbulent representation. Okay? We have to come up with an appropriate turbulent representations. Now, that is an advanced subject. Okay? So for you undergraduates, I'm not going to bore you in that. In fact, in our fluid mechanics, we have to take a separate course in turbulence to actually derive the turbulence models that can be applied to a given problem. Okay? But there are various turbulence models that can be applied. And so, yes, we need to determine whether the flow is laminar or turbulence so that we can apply the right turbulence model. We need to determine whether the flow is incompressible or compressible so that we can apply, based on the Mach number, we can apply the equation of state or not. We need to apply, we need to know whether we have a single or multi-phase system so that we can apply the correct cavitation model or two-fluid model in the solution of the CFD. You know, when you go into a lot of these softwares, you see, there are basically panels within it that tells you that, look, if your solution, if you are solving an incompressible process, just turn on the incompressible model part of the model. Okay? If you don't turn on or turn off the appropriate model, then you're not going to get the right solution. So that is all this is saying. I have to have a clear understanding of the nature of my flow so that I can turn off or turn on the right model in order to get an accurate solution. Now, if you are, of course, deriving that from scratch and solving it on your own, then your derivation, of course, you are taking that into consideration. But, you know, if not, then to accurately produce correct simulation results, you have to have a clear understanding of the phenomenon that is taking place so that you turn on or off any of these modeling features, okay, within your CFD program. Comments or questions? Yes?
So basically, all these models are integrated in the required software.
Exactly. Okay? A very good CFD program, okay, a very good CFD program like ANSYS has all of these integrated within it. Now, not all of them do. Okay? In the case where they don't, then you, the expert user, have to basically do it by writing your own user-defined routine that would be linked to the solution process. Okay? That is another subject. We are not going to go there. Okay? But all I'm saying is that, you know, and at the back of your mind, in designing any CFD problem, you know, you have to have a clear understanding of the physics of the problem so that you can model it accurately. Any comments? Yes?
According to some form of velocity distribution model, I can wonder to describe the velocity distribution.
Yes, your turbulence model basically describes the velocity model. And so, you know, some, you know, they call the large eddy simulation model. Some they call it Reynolds average, you know, kinetic energy epsilon model, and so forth. So it's basically a way of how the velocity is distributed.